So now, so far, we had taken ideal situations without any friction, and we would like to now consider what if there is friction, and then what happens to something that's oscillating. As you may imagine, if there is friction, the total energy will be decreasing, and so the kinetic energy will also be decreasing, and so it will move, the maximum kinetic energy will be decreasing, so it will be moving slower and slower and slower until sometime it will come to rest. And so here is our spring. Let's just take that. Here is the spring. And here is the natural position of the spring. We're going to take our mass, pull it down to the right, attach a mass to it, pull it to the right, pull it this way, here is x, and then let it oscillate. But then there will be some friction here. So when it moves this way, when it's on this side, friction is to the left. The same thing with the force of the spring, it's also this way, right? When you're to the right, the force of the spring is to the left, and but friction will also be to the left. And it's proportional to, it's related to the velocity because friction is always in the same direction as in the opposite direction to the velocity. So here is the original situation without the friction. We had the negative kx, that was the force from the spring. That's it, that was the only force, and that was equal to the mass times acceleration, which is the second derivative of x with respect to time. That was it. And put here negative k times x. But now we're going to add friction, and the friction will be proportional to the negative of the velocity. And that friction will be negative some constant b times the velocity. And the velocity is dx dt, and so we have this. So let's take everything to the other side. So I have m dx dt plus b. Instead of v, I'm going to write dx dt. And then move the kx to the other side. I have kx equal to 0. And you have this second order differential equation to solve. Now it's going to oscillate but then also decay. It will slow down. The displacement should be slowing down. So to solve this, it's very difficult to guess it if you just use sines and cosines the way we have been using it. And the way people solve this, they realize that, I don't want to get into it a lot, but let me just show you quickly, and if I have time at some point toward the end of the semester, I would spend maybe an hour on complex numbers. But for now, let me show you this. We had the sine of theta was equal to theta plus theta cubed over 3 factorial, minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, and then minus theta to the 7th over 7 factorial, and so on. And the cosine of theta was 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial, and so on. People showed the expansion of the e to the x will be 1 plus x squared, 1 plus x over 1 factorial, 1 plus x, let me just write it, or let me write e to the theta. E to the theta will be 1 plus theta plus theta cubed over 3 factorial, I keep skipping the even ones, theta squared over 2 factorial plus theta cubed over 3 factorial plus theta to the 4th over 4 factorial plus dot. And it seems like I'm adding, like somehow there are the odd ones for the sine and the even ones for the cosine, and somehow they're related. And it turns out that if you put an I here, e to the I theta, you will get the following. E to the I theta will be the cosine of theta plus I sine theta. where I is the imaginary number, or the complex number, the square root of -1. And you think exponential, it's related to sines and cosines. They're no way related, but turns out that they are. This is a great formula by Euler. You can look it up if you have never seen it. It's a great formula. It's something I think you will need next semester for Physics 230, or you will need, definitely for 231, you need to know about this. So what people did is they said, well, let's assume that the solution is of the form e to the I theta, or e to the I x t, and then, or e to the I omega t, and plug it here. And the nice thing about exponential functions is when you take the derivative of e to the x, you get e to the x back, or e to the t, you get e to the t back. If there is something e to the something times t, you just get that down. When you plug it here, the e goes away, and then it becomes an algebraic equation to solve, not a differential one. Anyways, the solution to this turns out to be x of t. I will just copy it from the book, because the book takes the attitude of, here's the solution, plug it into here and verify that it works. And if it works, it is the solution. If it works, satisfies the boundary, the initial conditions, then it is fine. Then it is the solution, which is fine. I mean, if somebody could guess it and it's a solution, then it is. It's a valid thing. But the problem is you can't always guess. It's difficult, so you need a more methodical, more step-by-step way to do it, and this is one of those techniques that is useful. So let me just write it down. Let me get my book. Turns out that e to the that x of t will have that inherent cosine, but it is equal to some amplitude, and then e to the negative b times t divided by 2m, and then times the cosine of omega t plus phi. Now what would omega be? Omega is equal to the following. Omega is equal to k over m minus b squared over 4m squared, don't want to copy it wrong, square root. And that's equal to, you see here the square root of k over m, or k over m is omega squared without this damping or friction. So this I would write just as omega 0 without the damping squared minus b squared over 4m squared, which looks good, because the reason it looks good is that if you take b equal to 0, no damping, this thing here disappears, and we should get the cosine of omega t plus phi. And so e to the 0, if b was 0, so this thing disappears, so you just have a times the cosine of omega t plus phi. But omega, if b is 0, this goes away, and you just have the square root of k over m, and it reduces to the previous simple harmonic motion. All right? And the way this looks like, let me just show you. If you graph this, you see this is decaying. This is going to 0, and this one fluctuates between +1 and -1. And so you have a function that looks like this. It starts here at some amplitude. As it oscillates, the amplitude will get smaller and smaller and smaller. This function here says it's really never 0. It's 0 only when t goes to infinity, but it decays. And the decay will look, sorry, it should, I should have drawn this one a little long. It should look like that. This here will be the e to the negative b t over 2m, this part. So it's the cosine, but enveloped or inside this decaying exponential function. Okay. All right. So if you have a mass on a spring, it oscillates, but then they get closer and closer to the equilibrium point until they end at the equilibrium point. farther from equilibrium point, a little closer, even closer, 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 until they get to the equilibrium point. So this is with damping. Now, if we want to calculate the total energy of this at time t, remember the total energy is 1/2. You can just, if it's all potential, it's just total energy will equal to the potential energy, which is 1/2 kx maximum squared. So this is x of t. The maximum x is just without the cosine, it's just this part. That's the maximum x. It can be, because the cosine, maximum value for the cosine is always 1. So it's just this part. So we know that x maximum is equal to a times e to the negative bt over 2m. And if you want x maximum squared would be a squared, and if you square this, it would be e to the, when you square something, it's just your e to the positive 2, and e to this number to the 2, you multiply the exponents, so the 2 on the bottom cancels, so it becomes e to the negative bt over m, and so the total energy would be just equal to the potential energy when it is maximum, which is 1/2 kx maximum, a maximum squared, so you get 1/2 k x maximum squared is this, a squared e to the minus bt over m. And you see the total energy is decaying. At t equal to 0, it is 1/2 ka squared, which makes perfect sense. You pull this spring, and it has only potential energy, and it's equal to 1/2 ka squared. You let it go, swings, still has some mechanical energy, but that mechanical energy is decaying, and this goes down here. It's going down. Now, tau, this thing here, you can write it as it's called the time constant, 1/2 ka squared, e to the negative t over tau, and this 1 over tau is b over m. So tau, 1 over tau is equal to b over m, and therefore tau is equal to m over b. M over b. All right. The longer the tau is, the less quickly it will drop. Right. So if you have a very large mass, tau will be longer, or if you have very small b, tau will be longer. Right. If you have very small b, it means you have very small friction, and so the energy will decay after a very long time. But if b is very strong, then tau will be very strong, and it will just decay. And it will just decay. All right, that's that. I want to just show you an example here. Just show you an example. So let's say you have a damped pendulum, and it is, so you put a 50 gram mass, and it swings on a 60 centimeter long, 60 centimeter string. So it's a mass, so it's just a simple pendulum. So let me draw it. Let me draw it here. Draw that. Or actually, let me try to do it in here so we don't forget. So here is the pendulum, here is the mass, here is the mass M, and this is L, that's L, and looks like that, and this is theta here, theta, and it's swinging back and forth, and with the pendulum, again, there is some friction, always, there is some frictional torque, and it will eventually come to a stop. And so since there is friction, then we will expect this will be a more accurate way to describe the problem here. So let me just write down L and M. So we have L is, the length is 60 centimeters and the mass is 500 grams. So L is 60 centimeters or 0.6 meters, 0.6 meters. And the mass is 500 grams, 0.5 kilograms, all right? And I want to just read the problem at once for you. So it says a 500 gram mass swings on a 60 centimeter string as a pendulum. The amplitude is observed to decay to its half initial value after 35 oscillations. And the question is, what is the time constant of this oscillator? And then what is the energy, or at what time will the energy have decayed to half of its value? So they say after 35 oscillations, the this pendulum here will have half of its initial amplitude after 35 oscillations. So when t is equal to 35, we have when t is equal to 35 oscillations, we get half of the energy, half of the displacement, or half of the amplitude. Now let's just think, for a pendulum, we have, first of all, the period for a pendulum. Let me maybe use the whiteboard as well. So the period for a pendulum is 2 pi L over G square root. So let's calculate the pendulum, the period. So we get, it is, I need my calculator again, which I always keep here. So the period will be 0.6 over 9.8 square root times 2 pi, which is 1.55 seconds, approximately. So 0.6 over 9.8 to the power 1/2 times 2 times pi. 1.555. 1.555 seconds. Now, x of t is equal to this. So let me write it. X of t is, or the amplitude. You see the amplitude itself, this is x, and the amplitude is what's in front of the cosine, right? This is the amplitude without the damping, but the amplitude with the damping is the whole thing, is what's in front of the cosine. That's how far you are from equilibrium, the maximum displacement from equilibrium. So let me write here the amplitude itself as a function of time. It is equal to the amplitude without the damping, and then e to the negative b over m. B over m is 1 over tau, so I'll write it as negative b over 2 tau. I'm sorry, negative t over 2 tau. T over 2 tau. All right? And they're saying after 35 periods, the amplitude is half of its original value. So the A after 35 periods, I think it was 35 periods, A after 35 periods, yeah, A after 35 periods. So when t is equal to 35 capital T, A is half of its original value. 1/2 of the initial value is half of capital A. All right? So let's see here. So on the left-hand side here, I have 1/2 of capital A equals e to the negative. T is 35 tau. T is 35 times tau, and tau is 1.555 divided by, I'm sorry, it's 35 capital T. T is 35 capital T. And divided by 2 tau. And I forget the A in front, so there is an A in front here. A in front. So the A cancels. And I want to find what tau is. So I have here 1/2 equals to e to the negative 35 times 1.555 over 2 tau. If you take the natural log of both sides, you have the natural log of 1/2 ln of 2 will equal to, natural log of e to the something is just e to the something, so I have negative 35, 1.555, yeah, it is 1.55, over 2 tau. Natural log of 2, natural log of 1/2 is a negative number, and there I have a negative, so it will be positive. So tau will equal to the following. So it will be times 35 over 2 over the natural log of 1/2. So it says here tau is 39.25. 39.25 seconds. 39.25 seconds for tau. So we have found tau, and the next question says, how long will it take for the energy to be half of the initial energy, knowing tau? Well, let me write down here. Let me just actually use the whiteboard. Here is the energy as a function of time. E is equal to 1/2 Ka squared e to the negative t over tau. Let's write it down. The energy as a function of time, that's total mechanical energy, it's 1/2 Ka squared, and then e to the negative t over tau. And so we would like, at some time t, the energy at t equal to 0, is equal to 1/2 of Ka squared. And then we would like E at some time t to equal to 1/2 of the initial energy, the energy at t equal to 0. Well, let's see. The energy at t equal to 0 is the 1/2 Ka squared. And the energy at time t is the 1/2 Ka squared e to the negative t over tau. Actually, I want 1/2 of that, so it will be 1/2 of this. So I want, at some time t, the energy will be half of the initial energy. So you get the 1/2 Ka squared, 1/2 Ka squared goes, and so we need e to the negative t over tau to equal to 1/2. And so take the natural log of both sides, so I have negative t over tau will be the natural log of 1/2. And remember, the natural log of 1/2, 1/2 is 2 to the negative 1. Negative 1 comes from the other side, so it's the same as negative the natural log of 2. You can try it. Put in your calculator the natural log of 1/2 and put the natural log of 2, and you will see they are equal except for a minus sign. So this and this, so you get t over tau would be the natural log of 2, and so t would equal to tau times the natural log of 2, and tau was found earlier to be 39.5, so I have 39.25 times the natural log of 2. That's t. So at this time, the energy would be half of its initial value. So let's multiply it by the natural log of 2. Put enter. 27.2 seconds. So after 29.2 seconds, the energy would be half of its initial value. And so that's that for damping. Now you can also have a driven oscillator. So this is with damping, so you move it and then you let go and you don't interfere anymore. So you just let the system do whatever. On the other hand, you can have a driven oscillator where you actually come in and push it, or maybe there is something that's pushing it, shaking the system constantly at some force. So you can have a driven oscillator. So you have the forces on it will be negative Kx for the spring, and then negative Bv for the force of friction, and then you can have also an external force, a driving force. So maybe somebody is interfering and pushing the system. So some other force, driving force. Somebody pushing. So let's say you have a kid on a swing, and you interfere and push the kid or the person every time they go and come back, every period you give them a push. There is some driving force. It's a force as a function of time. And that should equal to the mass times acceleration. And so if you move these to the other side, you just have the driving force. Driving force is usually periodic, usually something times something cosine something or sine something. And so your equation becomes the driving force on one side and everything else to the other side. So you get the mass times dx dt squared plus b times dx dt for velocity, and then kx. And you have to solve this equation. Now you cannot solve, I mean, you know these, but you cannot solve it until you know this one. And this is usually some sine or a cosine function. And as soon as you know it, you can solve that. And it takes some techniques from complex numbers. And the book doesn't get into it, and so I will not get into it, at least at this time. You will see these when you do circuits next semester, and you would have capacitors and inductors in a circuit, and you can also have an external voltage driving, and you will solve this in Physics 230. So you're not, this is not just specific to this class. You will also see it in the next semester. It turns out if the driving force has it has the same frequency as the natural frequency of that spring, you have what's called resonance, and they resonate, and then the amplitude of those oscillations will grow greatly, which is the same, similar to like if you have a kid on a swing. Again, back to the swing. So let's say if you just give them a push while they're moving away from you, then their amplitude will be higher and higher. They have more fun because they're rising. On the other hand, if you push them at the wrong time, if it's out of phase, when they are coming towards you, you give them a push, your push slows them down. You push at the wrong time, then they would start slowing down. But if you push at the natural frequency, if the swing has a certain omega, and you push exactly with that frequency or with that period, if they have, let's say the swing goes back and forth every 1 second, then you push every 1 second, you coincide with it, then the amplitude will grow larger and larger, and you have what's called resonance. All right, that's as much as I will say about this, and I will see you in the next videos where we will do end of chapter problems from this chapter. All right, I'll see you next time.